thank the organizers who did all the work for inviting me. So this is edge states in periodic and aperiodic systems. Put it up higher. How about now? Is that better? Hello? It's on. How about now? A little bit better? Okay. So let me just start by, I'd like to acknowledge many collaborators that I've worked with over the little more than 10 years on these problems, and also acknowledge people, many people in the room with whom I've discussed things and have benefited greatly. Special mention of a talk that will be given by Pierre Amenoagbadji on Thursday, which will be go into the details on aperiodic structures. Okay, so let's start slowly. So we begin with a Bravais lattice. We take two linearly independent vectors in the plane and look at all integer linear combinations of them. The dual lattice, K1 and K2, is in the dual plane, R2K. Dual lattice is given by this direct sum, where Kj dot VL are delta Ij. Then we have the Récanzone, which is a fundamental cell in the dual, which consists of all points in the plane which are closer to the origin than to any other point in the dual lattice. Okay. So the examples we'll see are, of course, the square lattice. A here is some constant, the lattice constant. It's the square lattice. There's the square Récanzone. The equilateral triangular lattice. Here the basis vectors are V1 and V2, written down here, the dual lattice vectors. The Récanzone in this case is a regular hexagon. And I'll call the top point capital K, the bottom point K prime, which is minus K. K1 and K2 are indicated here, the dual basis. Okay. And so next we'll look at the honeycomb lattice, which is not a Bravais lattice, it's a multi-lattice. We start with the triangular lattice, the equilateral triangular lattice, and we pick two base points, VA and VB, shown over here. And we look at the lattices, the triangular lattices with base point at A and base point at VB. And these distances are chosen so that what you get is this interpenetrating two triangular lattices. If you connect the edges, you have regular hexagons. Here again is V1 and V2. These are basis vectors at an A site, so they generate the A sublattice, and V1, V2 located at a B site, generating the B sublattice. Again, the Récanzone, because it's the underlying periodicity is with respect to the triangular lattice, is the regular hexagon with points K, K prime, etc. Okay, so from lattices now to two-dimensional materials. So a two-dimensional material for me here is going to be a Schrödinger operator with a particular kind of potential. Okay, we could be looking at other operators, like the Maxwell operator, but we'll look at Schrödinger operators here. So a bulk material, bulk refers to the infinite structure, the infinite periodic structure with no defects in it. So we have minus Laplacian plus V of x. V is a real function, real valued function, and V is going to be periodic with respect to some Bravais lattice lambda, like that. And sort of the motivating example is really the properties, the wonderful properties of graphene, shown here as a honeycomb arrangement of carbon atoms that extends to the macro scale. We'll be interested in edge states, so those are going to be a kind of state that lives in perturbations of a bulk material. So you take the infinite honeycomb structure or the infinite square lattice structure or the infinite triangular lattice structure, or more generally, you could take the infinite Kagome lattice structure, anything, and you could introduce different kinds of perturbations. And these are typically going to be these will be spatial perturbations, and they will be non-compact, spatially non-compact. So, for example, a sharp truncation of the medium, or a domain wall. We'll talk about that in great detail. These are kind of line defects. And also, I'm interested in spatially non-uniform deformations as well, where, okay, so some examples. Sharp termination, we'll just think schematically like this. H is minus Laplacian plus V, and so you have some eigenvalue problem for Laplacian plus V on this side of some line defect, and V is identically 0 out here, okay? So, and then you have to have some kind of conditions across an interface. So the sort of the motivating examples in graphene are truncations along a so-called armchair edge or a zigzag edge. And these are shown really as graphs, but think of these little dots over here as being radially symmetric potentials that are centered at those vertices. Okay, then you have a V of x formed by these. And so you could think of this as if things extend infinitely to the right and infinitely up and down, then what you have is a honeycomb half space with a kind of different kinds of terminations. Okay. Another example where this comes, just to show you, so we're not only interested in condensed matter examples, but more in what are sometimes called metamaterials. So here's an example of artificial graphene. So in experiments beginning with Segev and Récanzone and many others since, people have looked at honeycomb arrays of optical fibers. So now the Schrödinger equation, linear or even nonlinear, comes out of here arises as from the Helmholtz equation in the so-called paraxial regime. And the experiment that's done is they take a laser, something like this, and they illuminate the interface. If this were an infinite array in all directions of optical fibers, then what would happen is the light would propagate down, say at low amplitude, it would propagate down according to some honeycomb potential and diffract in a manner which sampled the block modes in the regime where you're exciting. So if you were near the so-called the Dirac point, you would see Dirac type dynamics, or if you were near a generic point, you might see something more dispersive. Anyway, in any case, in these experiments, often the edge is illuminated, and one looks at so-called edge states, which propagate down the fiber and then around the edge also. We'll come back to such things a bit later. Okay, and again, these things have a meaning also in the nonlinear regime, where this equation is also called the nonlinear Schrödinger-Gross-Pitaevsky equation, because it arises as a mean field limit in many body quantum systems. Okay, so those are sharp terminations, and here's a domain wall. So schematically, a domain wall is you've got one bulk periodic structure way out on the right at plus infinity, and one bulk structure way out on the left at minus infinity, and then there's going to be some transition zone. Our transition zone will be smooth, and in this regime, we'll call this the domain wall regime. And here's a sort of a numerical plot of an example where you have something which is perfectly periodic over here, a V minus, perfectly periodic over here at infinity, V plus, and you see that there's some kind of a phase shift or dislocation along this boundary. This is the edge over here, or the domain wall. Okay. Please stop me if there's any terminology or anything unclear. Yeah. Okay, and then finally, here's a non-uniform spatial deformation. I hope that one can see this. This is a very very nicely fabricated two-dimensional photonic crystal. This is it's a very, very thin layer of semiconductor where someone came with an etching device and made roughly triangular holes. So this is a nice triangular lattice of holes, and there the experiment is to excite this slab, this very, very thin slab, a nearly two-dimensional medium with light in different wavelengths, and to see how the light spreads out. This is the undistorted medium honeycomb structure, which we'll talk a bit about, and this is a distortion. This is an example of a non-uniform distortion. And one of the things that one can derive in this setting is where here this was done for TM. For TM, Maxwell is a so-called pseudo-magnetic effect. So here the bulk structure, the unperturbed bulk structure, is just a div grad, where C here is 1 over epsilon, the dielectric constant, and the deformed structure is C tilde, where C tilde is C composed with some non-uniform deformation. Like that, okay. And if delta is small, then one could do some kind of homogenization analysis to get effective equations. Okay.
So why pseudomagnetic?
Okay, I'm not going to go into this in detail, but it's called pseudomagnetic for the following. So there's no magnetism here. Okay, this is just light in a structure, and there's no magnet in the room. But what happens is when you deform, you see, up here, in this problem over here, there is an effective dynamics given by a Dirac equation, which governs the propagation of wave packets. And in the deformed structure, instead of a Dirac equation, you get a magnetic Dirac equation. And the magnetic, there's a gauge potential, a magnetic gauge potential, which is computed from the distortion. So what happens is, in this case, photons behave as though they were charged particles in a magnetic field. Okay. If there's time, I can say a little more about that. Okay, so now more for the mathematical setup. Is there a clock? There's a clock, okay. Flow K block theory. Okay, so just to set certain basic definitions and notation, here's my operator. It's a real valued potential V, which is periodic with respect to a Bravais lattice. For every K in the Brouin zone, we consider the K pseudoperiodic eigenvalue problem, H phi equals E phi. Phi satisfies the PDE, but it also satisfies a boundary condition, the pseudoperiodic boundary condition. We say that phi is in the space L2 subscript K if phi is square integrable on any compact set and satisfies this this condition, this pseudoperiodic condition, for every V in the Bravais lattice and almost everywhere in X. Okay. So because the potential is periodic with respect to the lattice lambda, H maps, say, C infinity L2K function, C infinity pseudoperiodic functions to pseudoperiodic functions. So we could think of H as acting in the space L2K, and we'll denote that operator by H sub K. H sub K is just H on the space L2K. It acts invariantly there. This is a self-adjoint operator. It has compact resolvent, these self-adjoint boundary conditions, and so there is a sequence of eigenpairs. Okay, these EB of Ks are real valued functions of K varying over the Brouin zone. So think of K moving in a hexagon or a square, whatever the Brouin zone is. So these are nice Lipschitz continuous functions. For each fixed b, it's a Lipschitz continuous function. And phi b are the corresponding Bloch modes. Here, everything is listed with multiplicity. And so while these are Lipschitz continuous, the phi b's can be pretty nasty. They can actually be multi-valued. So let's look at so these maps, okay, as I said, have graphs, and these graphs are called dispersion surfaces. Okay? So think of the domain, the Brouin zone, with an infinite set of surfaces that sit above it. And some of these surfaces can touch. The collection of all of these eigenpairs, as B varies and as K varies over the Brouin zone, is called the band structure of the operator H, of the bulk operator H. And there's a completeness theorem that says if you take any function in L2, then you could write it as superposition. You project every f onto each Floquet Bloch mode. You integrate with respect to k, and you sum over all the bands. Okay, and these coefficients over here, I'll call this maybe fb tilde of k, will be called we'll call this the Beeth Floquet Bloch coefficient of the function f. Okay. And this sum makes sense in L2. I look at partial sums, subtract, take the L2 norm and pass to the limit. Converges in L2 of the plane. Okay. All right. So now I want to get a little bit more specialized. I want to look at interesting crystalline media. We'll be looking at two-dimensional bulk media with symmetry. So first, some symmetry operations. Parity inversion, P, complex conjugation. In the context of the Schrödinger equation, complex conjugation is often called time reversal symmetry. However, for Maxwell, it's not, it's a different notion, is time reversal. And then we have a rotation operator. We take F, and we apply a rotation matrix by theta, rotation by an angle theta, this 2 by 2 orthogonal matrix. Okay. And in what I'll discuss, I'll always assume x equal to 0 is the origin of coordinates with respect to which we act with these symmetries. And then finally, there's the translation operator, which is just translation by elements of the lattice. Okay, so continuous bulk media, which are periodic, have the I'm interested in, here I'm going to introduce continuous bulk media, which are going to be modeled by potentials which have the symmetries of the discrete lattice. So V of x is will be called a square lattice potential if V is even, if it's real, if it's rotationally invariant by 90 degrees, and if it's periodic with respect to the square lattice. That should be Z2. That is, the operator H commutes with P, C, rotation by pi over 2, and all the translations. And the same thing would hold for the Maxwell equation. Let me just say that in Maxwell's equations, of course, the epsilon is not always a scalar. It's sometimes a tensor. And so there'll be a variant of this for where you have to conjugate the inverse of the dielectric tensor with the rotation matrix. Second example, a honeycomb lattice potential. We take the triangular lattice. Something's a honeycomb lattice potential if it's, again, even, real, now rotationally invariant by 120 degrees, and translation invariant. That should be for all V, not in Z, not in Z2, but in the triangular lattice, equilateral triangular lattice. So here, H commutes with PC, R 2 pi over 3, etc. And this V again is in the triangular lattice. Okay, so those are honeycomb Schrödinger operators now, and similar discussion for for, say, T.E. Maxwell. Okay. So what's an example of a honeycomb potential? Well, I could take a radially symmetric function, V0, which is, say, compactly supported, and I could just place them at the vertices, sort of center those radially symmetric functions at the vertices of whatever lattice. So I could take this would be a square lattice potential, this would be a triangular lattice potential, and this would be a honeycomb lattice potential. So you just imagine circles rather than dots sitting at the vertices of whatever lattice. And alternatively, you could represent these as Fourier. These are Fourier. Anything satisfying such conditions imposes constraints on the Fourier coefficients. So here's a general Fourier series of a periodic function in the plane, but now we could if K1 and K2 come from one of these lattices, there'll be constraints, of course, on the Fourier coefficients given by these conditions. Okay, and one could write those down. Yeah. And there's a connection between these two, of course. If I could always represent these as Fourier series, and that's really what the Poisson summation formula is about. It takes you between these two descriptions. Okay. So now let's talk about band structure degeneracies. So these are going to be cases where the band dispersion surfaces can touch. And a lot of the action in quantum materials happens around these degeneracies. So the simplest example is a periodic, so we'll look at a one-dimensional periodic potential, and the simplest potential is the zero potential. If I view the zero potential as something which is 2 pi and plot the bands over the Brouin zone, which is here an interval from -1/2 to 1/2, then this is a standard band structure construction where you could realize the band structure as the union of parabolas modulo the dual lattice. So here's a parabola. There's another parabola over here, but I have to fold it over everything into the Brouin zone. So here you see the first band function. This is the first dispersion curve, second dispersion curve, third dispersion curve, fourth dispersion curve, etc. Infinitely many. And they all touch. They touch at eigenvalues of multiplicity 2, and they do so over these special points only, between at 0 or at 1/2. -1/2 is equivalent to 1/2. It's a fact in one space dimension that for any periodic potential, the dispersion curves are monotone away from these points of so-called high symmetry quasi-momenta. This is not the case in higher dimensions. Okay. Now if I perturb the potential to have a small periodic potential, this is sometimes called Hill's equation, then what happens is these degeneracies split. They open up generically. So for example, if V hat of 1, the first Fourier coefficient of V is non-zero, then you'll get a splitting at these points, okay? And the splitting will, depending on the regularity of the potential, the splitting may occur like order epsilon, epsilon squared, et cetera. You get a gap in the energy. So the spectrum is actually the spectrum is the set of all is the image of all of the band functions. So it just sweeps out intervals now with gaps. Here the spectrum, of course, is that of the Laplacian. It goes from 0 to infinity, and here it's a semi-infinite interval with gaps. Okay. 2 dimensions. So band structures with 2 dimensions. So my examples will be the honeycomb lattice, square lattice potentials, and then a square lattice potential which is strained in some uniform fashion, where here T is a now a constant matrix, 2 by 2 real constant matrix, which is not orthogonal. If it were orthogonal, I would just rotate the lattice, but you could think of this as being some kind of a strain of the medium, a small strain of the medium. Okay. So in the honeycomb case, these are the first 3 dispersion surfaces of a typical honeycomb lattice potential. And what you see is that in this case, the first 2 surfaces touch over the vertices of the Brouin zone, and they have a, if you turn up the resolution, you see roughly a conical behavior. Okay. So for a typical honeycomb lattice potential, here the first and second dispersion surfaces touch at Dirac points, and Dirac points are points where the 2 dispersion surfaces, let's call the upper one E plus, the lower one E minus, they touch in a right circular cone. And so the significance of this, of course, is that if you look locally here in flow K block space, if I construct a wave packet which is spectrally concentrated around the energy of the Dirac point, E is the vertical axis, and at quasi-momentum around one of these vertices, then this wave packet will propagate according to some kind of a wave equation. And that wave equation one could work out as an effective Dirac equation having this form. Vd over here is just the aperture of the cone, and sigma 1 and sigma 2 are the standard 2 by 2 Pauli matrices. To the point about, to the question about non-uniform distortions, what happens is if the honeycomb is distorted, as I showed on the previous slide, then this operator, this is P1 and P2, gets replaced by P1 plus A1 and P2 plus A2, where A1 and A2 are effective magnetic potentials, which can be computed from the formula for the distortion. So you go, then in that case, from an effective Dirac equation to an effective magnetic Dirac equation. Here's another example from the, so in 2D square lattice media, take square lattice potentials. Okay, so that's a intensity plot of a square lattice potential. One finds that there are quadratic, not conical, but quadratic touchings of dispersion surfaces over the vertices of the square Brouin zone. Okay, and then further, if I make a distortion, so this is now a linear distortion, like linear distortion. Like in a previous slide, basically V composed with T inverse, where T inverse is a constant matrix, not orthogonal, then what will happen is this quadratic touching will split into 2 Dirac points, which might be a bit surprising. If I have 2 surfaces that touch, that touch each other, you'd think that if I perturb the system a little bit, then maybe one might pass through the other, and I would get an intersection along a curve. But this is a self-adjoint these are self-adjoint Hamiltonians, and self-adjointness and symmetry forces this deformation from here to here to give you touching still at points, locally at points, and here they are conical. And if you blow up, what you see is that the cones are not right circular cones as they were in the honeycomb case, but rather they're tilted in elliptical cones. And there's some effective Hamiltonian associated with this picture. These will be Dirac Hamiltonians associated with each of those touchings, or a matrix second order operator, not of Dirac type, up here. Okay. So I want to say something about why the vertices of the Brouin zone, and let me look at, to say something about the origins of Dirac points, because they're really, so critical to things in this field. So if I look in the honeycomb case, there the symmetry is 120-degree rotation, so V is invariant under that rotation. Again, here is L2K, and HK is the operator H acting in the space of pseudoperiodic. Yep. Yep. So this is, suppose T is, chalk. So I look at, so T is, say, 2 by 2, and let's assume that this has small norm. And I look at V composed with T inverse. Okay, so anything like that. All right. So there'll be some genericity conditions, which you'll need some coefficients to see this at leading order. But if this perturbation, say, is size epsilon, then you'll get Dirac points, a distance square root of epsilon from each other. Hmm? Oh. Did I? Oh, sorry. Yeah, it's exactly not that case. I don't want it to be orthogonal. I mean, the orthogonal case is trivial, right? Okay. Thank you. Sorry about that typo. Sorry about that confusion. Yeah. Is it clear now? Okay. Okay. All right. Yeah. Right. Basically, you make a change of variables. When you make a change of variables, you go from the div grad goes into the push forward of div grad, and so you get T transpose T, divergence T transpose T grad. Okay. And then you add and subtract, and that gives you this. Then it becomes a small perturbation of the Laplacian. Yeah.
And so if you expect to have Dirac current for identity minus T transpose T small, don't you expect it to have a generated for it? Don't you expect it to have it also generated for it?
Yeah, I'm not so sure what happens for all T as you get I think there's a good chance that this is true. In fact, numerically, what happens is as you take large distortions numerically, I was wondering whether maybe you could get Dirac points to collide and to annihilate. But we don't see that. That's a good question. Yeah. Thank you. Yeah. Okay. So why do the degeneracies appear at the vertices of the Brouin zone? So we have, there's this, and the key to it is that the following simple proposition. If you look at this rotation map, you ask, when does it commute? When does it commute with HK, the operator acting in the space L2K? And the answer is it commutes exactly when K is a vertex of the Brouin zone, modulo the dual lattice. In other words, there's an extra symmetry of the eigenvalue problem when the quasi-momentum is chosen to be one of those vertices of the Brouin zone. Okay? And such vertices are called high symmetry quasi-momenta. Okay? So recognizing that, so now since we have an operator which commutes with the Hamiltonian, and in this case its cube is equal to the identity, and the spectrum of an operator whose cube is the identity is going to have eigenvalues 1 tau and tau bar. These are points in the essential spectrum of this operator. Then you could break L2 into an orthogonal sum of L2 K1, the L2K tau and L2K tau bar spaces, where L2K sigma is just, sigma here is an index, and it's just all L2K functions which give you a factor of sigma, 1 tau or tau bar, when you apply the rotation to it. Okay. So that's the first observation. Now, there's a sufficient condition that one can write down for the existence of Dirac points. So you have this triple direct sum, orthogonal sum, in terms of the spaces 1, tau, and tau bar. So the spectrum of the operator H acting in that quasi-momentum, high symmetry quasi-momentum subspace is going to be will be equal to the union of the spectra in these individual subspaces. And the claim is that the following happens, that there is a triple eigenvalue. You could find, for example, a triple eigenvalue of the Laplace operator when lambda is equal to 0 in that space. And then that triple eigenvalue under perturbation, as you crank up lambda, splits into a simple eigenvalue and a double eigenvalue under some kind of a Fourier coefficient condition, analogous to what I mentioned in the one-dimensional band structure problem. So for small lambda, one can basically do analytic perturbation theory of simple eigenvalues in each of the subspaces, and be able to check the sufficient conditions on the previous slide. So those conditions are that H have an L2k tau eigenvalue of multiplicity 1, an L2k tau bar eigenvalue of multiplicity 1, and that at this eigenvalue ED, there is no L2k1 eigenvalue of that space. And furthermore, this number, which is called the Dirac or Fermi velocity, should be non-zero. Okay, this is if you have the phi and phi 1 and phi 2 are the corresponding eigenmodes that correspond to the L2k tau and L2k tau bar eigenvectors respectively. So under these conditions, you have this. You can prove this this local dispersion picture plus information about the eigenstates. Okay, and to see, just so here is the calculation. I guess I mentioned this a little bit prematurely. I skipped over a slide. What I want to do is find a multiple eigenvalue, and that's easily done for the Laplacian. If I look at Laplacian, if I set v equal to 0, then notice that these three vertices, these three equivalent vertices of the Brouin zone, they're related by rotation by 120 degrees, give rise to a triple eigenvalue with these corresponding Floquet-Bloch modes. And moreover, because of the high symmetry property, the L2k star spaces corresponding to these 3 points are equivalent. It's the same boundary condition by the symmetries of the lattice. And it's easy to check that the multiplicity is exactly 3. So now you have, so now the second claim, so you have a triple eigenvalue, but that's not how you want to look at it. What you want to do is take appropriate linear combinations of these. So three different linear combinations, one linear combination here, one linear combination here, and one linear combination there. So those linear combinations are simple eigenvalues in these respective spaces. And so that you could then do elementary analytic perturbation theory of simple eigenvalues. You no longer have to worry about degeneracies and establish this picture that you get a double eigenvalue here in these spaces and a simple eigenvalue here under a Fourier non-degeneracy condition. And this is how you verify the hypotheses for lambda small. And then for lambda large, you have to show some kind of persistence of the properties of those sufficient conditions, and that requires analyticity arguments, which establish that you could satisfy the conditions except for lambda except for a bad set, a discrete set of lambdas coming from analyticity considerations. There's a very nice recent general approach that doesn't only cover the honeycomb lattice, but really very, very general situations, which treats this argument by Alexei and his recent student, Curtis Lyman. Okay. Okay, so now I'll talk about edge state localization at domain walls. So what is a domain wall? That's going to be some interpolation, right? Remember, across some zone between asymptotically periodic materials. And an edge state, okay, so this is going to be, this edge over here will be a direction of translation invariance. So that direction is going to be, an element of the period lattice. So an edge state is a time harmonic solution of the eigenvalue problem, h psi equals e psi. H delta domain wall psi equals e psi. I'll tell you what delta is in a moment. It'll be a small parameter, which is plane wave-like. It's going to look like it'll be propagating along the interface, and it'll be exponentially localized transverse. Looks like that. So there's going to be I'm going to explain how we write down the Hamiltonian. It's in 3 steps, and it's motivated by sort of a heuristic discussion in a paper by Haldane and Ragu from around 2006, 7, something like that. So here are the 3 steps. You start with a bulk problem. This is the bulk honeycomb, which has Dirac points, as I explained, over the independent k and k prime points of the Brouin zone. And there, the spectrum in a neighborhood of the Dirac energy is continuous straight through, right? Because there's no gap. It's a semi-Bandel point of 0 density of states right at the Dirac energy. And then what I want to do is I want to take the bulk and I'll perturb it by a symmetry breaking perturbation. My perturbation here will be one that breaks time reversal symmetry or complex conjugation. So here it is. Sigma 2 is the matrix Sigma 2 is this matrix. So I'm breaking complex conjugate invariance, and I take plus and minus on opposite sides, and I want A of x to be in, I didn't write it here, but it's going to have the same symmetries as V. It'll be even, and also lambda periodic. This is a kind of magnetic term. It's in photonics, it's called the gyromagnetic effect, but you can rewrite this so that it's essentially like a quantum magnetic Hamiltonian as well. So, so now that I've broken time reversal symmetry, the cones open up. Okay, so I break the Dirac point, and now there's a spectral gap there, at least locally. And then finally, I want to smoothly connect these 2 Hamiltonians on one side or another. Okay, so I have here's the triangular lattice, and I want to pick a direction, and I'll write that direction as V1 hat is equal to V1 plus R V2, where R is rational. So R is going to be B over A in lowest terms, where B and A are integers. And V2 will be the usual, the V2 of the triangular lattice, and then they're going to be dual vectors. Here is R again in K2. And then there are different cases. There's the case where V1 is rational, like this one. That's like the zigzag edge. And here's an irrational edge. It's, the medium is not translation invariant along with respect to any lattice vector for an irrational edge. And Pierre will be discussing this case. But for now, let's stick with the rational case. Here is the domain wall Hamiltonian. And my interpolation is going to be achieved via what we call a domain wall function. It's something that's like hyperbolic tangent. It transitions from between -1 and 1 as x, a slow variable, because there's a delta here, goes from minus infinity to plus infinity. Okay, so this is the type of Hamiltonian. Again, it's going to be a smooth and slow interpolation between asymptotic Hamiltonians, H plus, H delta plus, and H delta minus, where corresponding to putting kappa identically equal to 1, and K2 hat is that dual lattice vector, which is perpendicular to V1 hat, which is the direction. Okay. And this operator over here is translation invariant with respect to V1 by the standard relations between the K hats and the V hats. Okay, and all right, and here's the statement that asymptotically the Hamiltonian looks like these gapped Hamiltonians at infinity, and we're going to be in a situation, we're taking a situation where the gaps overlap or even agree at infinity. The energy gaps agree. Okay, so because of the translation invariance, there's going to be some parallel quasi-momentum. You could think of K parallel as like the propagation constant of a waveguide, of the waveguide. So you can decompose L2K parallel. You can decompose the Hamiltonian into the direct sum of operators, which are parameterized by K parallel. So each of these operators acts in a space L2K parallel like this. Okay. So these functions actually this acts on functions which are I think of these operators as acting on cylinders where there's a non-compact direction, which is the direction transverse to the edge, and a periodic or pseudo-periodic in the compact direction. Okay, so L2 of the cylinder. And then, so the claim is that the bands, for such a Hamiltonian, you'll have edge state curves. So what happens is the gap will be filled with edge state curves. So you have continuous spectrum all the way. I shouldn't say continuous spectrum. So I get spectrum all the way through the Dirac energy in this case, but in a neighborhood where the bulk gap was, they're going to be edge states. The edge states are going to be, these are every point along here for ranges of parallel quasi-momentum in a neighborhood of these points will correspond to states which are exponentially localized, transverse to the edge. Now, just a remark that since we're breaking time reversal invariance, the bands acquire a topologically non-trivial character, and there is a principle called the bulk edge correspondence principle, which can count the number of curves in an appropriate sense, in the sense of spectral flow, that traverse the gap. So see the lectures of Guillaume and Alexei for discussions on that. So there's a theorem, okay, which says that you have this situation, okay, this goes on. And a key hypothesis in that theorem is that the bulk operator, the bulk honeycomb that you start with, satisfies a semi-metallic condition, or so-called no-fold condition. Along an edge, it's an edge-dependent condition. It depends on the direction of the line defect. And it says that along a distinguished quasi-momentum line, which depends on the direction of the defect, the bands can touch energy ED, the Dirac energy, only on the high symmetry quasi-momenta, K or K prime, modulo the dual lattice. Basically, this condition ensures that a small symmetry breaking perturbation opens an appropriate spectral gap to give you these to allow for these exponentially localized states. Okay, so just a comment about how, oh, I better step it up here, about how the scheme works. So the edge states, because the Hamiltonian, taking advantage of the multi-scale, the two-scale structure of the Hamiltonian, one finds that the edge states have a two-scale structure. They're going to be slow modulations, slow transverse modulations of the degenerate block modes associated with the honeycomb, and the energy will be slightly perturbed. So H plus and this should be phi1 and phi2, phi1 and phi2. And this vector alpha1 and alpha2 consists of exponentially localized functions. I've written, here what I've done is I've written the result down for exactly this parallel quasi-momentum that sits right at the center over there. So the one with energy roughly ED. Okay. And these slow modulations, so these are like plane wave states, and these alpha1 and alpha2 are exponentially decaying in the variable transverse to the defect, and the transverse localization is governed in this special example by the kernel of a one-dimensional Dirac equation. And it's the fact that the domain wall function transitions from -1 to 1 that ensures that you have an exponentially localized state. So if you didn't transition between plus and minus at plus and minus infinity, you wouldn't get this kind of kernel. Now, the ingredients of the proof are, first of all, one looks at the multi-scale, one can make a multiple scale expansion to any order, but let's look at it just out to first order. That gives you an approximate solution. So I can construct a function of this type such that this pair over here is an approximate solution, approximate eigenpair. And then you decide what to do. And one approach, which was originally Pfefferman and Lee Thorpe and I approached it a little bit differently, but Alexei had the idea to use the quasi-mode strategy, which is based on a simple lemma in spectral theory, which says that if you have a very good approximate eigenstate, and the energy is in a spectral gap, right? And furthermore, that the energy that you have is sufficiently well separated from other eigenvalues in the gap, then nearby you have a genuine eigenstate, right? So, you know, if it looks like a duck and quacks like a duck, then it means there must be a duck nearby, right? So, so this is the quasi-mode strategy, and it can be used because in the rational case, because under the no-fold condition there is a spectral gap. But it turns out that for irrational edges, there is no spectral gap. And so we'll proceed. I'd like to say something about a different strategy now, okay? Which is a more direct strategy connected with what Pfefferman, Lee Thorpe, and I did. And it turns out that that strategy generalizes to the irrational case. So here it is. You start with the approximate solution plus an error. You write the solution and its you expand the eigenfunction and the eigenvalue, and you have to determine this upsilon delta and tau delta. These are correctors. They're to be constructed and estimated. And remember, from the completeness theorem of Floquet block modes, we could write the corrector. See, this is supposed to live in the space L2K, so we could write it functions in the space L2K as superpositions of the block modes, where now, because we're looking at functions on the cylinder, functions which in one direction are pseudo-periodic and localized transverse, what I do is I want to construct these as superpositions of block modes over appropriate quasi-momentum slices. So in the case of a zigzag edge, it corresponds to this momentum slice. I integrate over all the block modes, these lines parameterize the block modes that participate in constructing the pseudoperiodic, the K-parallel pseudoperiodic along the edge corrector. And when R is equal to 1/2, it looks like this. Okay, so the period is longer, so you visit more of the band structure. Okay, and so for any rational, you would get such pictures. All right, the bigger the denominator, the more such lines. Okay, and then you have to study the corrector. So you have to, you plug in, you write down the equation for the corrector. There's a term like this, plus lots of other stuff. This, of course, is small because you've chosen a good approximation. And now you have to invert this. I want to construct upsilon delta. I have to invert this, but the thing is that this gets very small, right? Notice that the domain wall Hamiltonian is a small perturbation of the bulk. It's size delta. That means that there is a spectral gap of size delta about the Dirac energy. So this is almost 0. And so this, a bit more precisely, this corresponds to quasi-momenta along those slices which come near the high symmetry points of the Brouillon zone. So again, I'm worried about near here and near here in the bands that cross, in the Dirac bands. So, okay, so it's natural to decompose L2K parallel into quasi-momentum components that are near the Dirac points and far away from the Dirac points, okay? Where there's, in terms of the small parameter delta, near is defined in terms of the small parameter delta. And at this point, I want to point out that if you look at this spectral projection, the near spectral projection onto your ansatz, the leading order piece, it's the spectral support of the approximation of the thing that came out of the formal multiple scale analysis is almost entirely in the range of the near projection. Okay. Okay. So the projection, more precisely, is you want to sum over the intersecting bands. And then you have to exclude small neighborhoods. The near part actually has these components over here. And the far part contains the segments outside of these. Okay. Oh, excuse me, I wrote outside, I meant inside over here. So the near part consists of things in a neighborhood of, and the far part is things complementary. It's exactly the other. This should have been inside. Okay. So this is, yeah. I wrote things in reverse. Okay. So near and then far on the segments. Okay. And so you could write this eigenvalue. You could write this now as a matrix problem in terms of projections onto the. You could write it as a problem in this direct sum Hilbert space. Running out of time. And well, the point is that with this decomposition, the far part is invertible. And so therefore I could solve for the near part, I could solve for the far part in terms of the near part. This is a linear map. And I get a non-local, a closed, so after solving by Shor complement, I could solve for the far part in terms of the near, and then I get a closed equation for the near part. And this has to be solved asymptotically. I won't go into the detail, there's some scaling, but in the scaled limit, what happens is that the effective Dirac operator arises, and you could use the properties of the effective Dirac operator to solve this asymptotic equation, and then you could reverse the process. This gives you the near part, then you could construct the far part because you had this invertible linear map, and then the solution. Okay. Now, just in the last couple of seconds, let me just remark on the irrational case. So remember, in the rational case, I have to integrate along these quasi-momentum lines for a rational edge. But there's no block theory in this case. So what do I do in the irrational case? And the strategy, going back to Pierre's earlier work, is to realize the quasi-periodic operator acting on L2 as the restriction of some lifted operator, okay, some augmented operator. So here is the augmented operator. One introduces a parameter S, so that's now a new dimension, a third dimension. If you will, it's a dimension that's transverse to the plane, transverse to the physical XY plane, and the potential is not changed at all. It's just this piece over here. So this is the lifted operator. And the idea is that, the point is that this lifted operator is actually translation invariant. It's been constructed to have translation invariance in 2 dimensions. Okay. And then there's a third dimension, which is S going to infinity, which is going to be the cylinder direction. So what we could do is we could solve this in this lifted setting. We study the augmented eigenvalue problem. We talk about augmented edge states, which have 2-dimensional two-dimensional actual periodicity, and then a decay condition away from some plane in some virtual third dimension. And then the idea then is to construct these edge states and then restrict to S equal to 0, show that these have a regularity, a continuity with respect to S, and then conclude that you have edge states in the original 2-dimensional structure. But here's the central issue, is that once you're in this 3-dimensional picture, you have to integrate over block modes. But now what you have is the quasi-momentum set that you have to integrate over is actually dense in the Brouin zone. Okay, so there are so what method requires is 2 applications of the Shor complement, and this is my last slide. First of all, let's take an alternative Brouin zone, which is, say, a diamond where K and K prime are not at vertices, but rather in the interior. And then we have to look at neighborhoods of K and K prime, where these are dense. And the first thing is to make a reduction to a very small neighborhood. That requires some kind of a resolvent expansion, where now the Dirac operator that appears here is Dirac with 2 underscores, and this is actually an infinite block diagonal Dirac operator which has discrete spectrum, and each one has discrete spectrum in its gap, and each Dirac operator corresponds to one of these stripes that passes through a small neighborhood. So this block diagonal operator has dense point spectrum, actually, in a spectral gap which is common to all of the Dirac operators. And then one has to make a further reduction to a single stripe. There's going to be another Shor complement Lyapunov-Schmidt reduction to a single stripe, and that's where it matters what the rational number is. And so at this point, one has to impose what's called a Diophantine condition, which is, in some sense, most irrational numbers have this. It means that the irrational number is poorly approximated by rational numbers. So with this additional condition, you can make that second Lyapunov-Schmidt reduction to the single stripe and conclude. So, and that will be the topic of Pierre's talk. So, thank you. Okay.
All right, we have time for one question before I go on break.
You said in the last slide that you have to have this Diophantine property for the irrational numbers, for the irrational guy that you have there. What happens whenever you lose that Diophantine property?
Okay, so those are what are called Liouville numbers, and those are numbers which are very well approximated by rationals, and that's a more resonant situation. Think of it that way. It's just a, so this is a kind of non-resonance condition. It shows that there's an interplay. You see, this appears, this combination appears in a denominator. When you do this Shor complement reduction, you have to invert an operator. And if you look at its Fourier series, it involves so-called small denominators. So you get something that's very, for a rational case, this could actually even be zero. But for the irrational case, it's never going to be zero. But it might get small. It might get small very, very quickly. You don't want that, okay? And what happens is it's an interplay between the operator, which has this kind of growth due to such a condition, and the smoothness of the function that it acts on, because there's actually it acts on smooth things, so that even though the denominator is shrinking and hence the quantity is growing, smoothness in the sense of Fourier gives you some kind of a balancing effect to make it work. Yeah.
Thank you.
Yeah.
All right, let's thank the speaker one more time. Thank you, Michael.